Hello and welcome. If you are fascinated by the neural architecture search as much as we are, you are going to want to hear about our latest research. In today, designing deep neural network for specialized tasks is more critical than ever. NAS is a game-changing technology that automates this process, but currently, most NAS methods require to iteratively search on the manual design search space. You are either limited on this high-level manual design search space, or you will spend a lot of time to search on the large search space. What if we can directly generate architectures that satisfies user need and only provide these promising architecture candidates for the NAS to search, which could significantly reduce the search cost? In our work, we proposed a new method that allows us to generate neural graphs based on the user input or the reference model. To break down, our work has following contribution. Firstly, we enhanced the current zero cost, or called zero proxy, extend them into the multi-dimensional vector. This allows for us for a more nuanced understanding of new network graphs. Next, we introduce semi-supervised learning for the graph variational autoencoder, or GVAE, to encode graph into the latent space efficiently. This helps us to navigate the architecture design space without compromise. We also leveraged a unique model we call the conditional continuous normalized flow to explore on this latent space. This results in the efficiently generate candidate architectures that satisfies the user's need. Here is the overview of our approach. We start with training a graph autoencoder with the triplet loss in a semi-supervised manner. In our latent space, the model with similar performance or similar cost should clustering together in this latent space. Then we train a matrix predictor to predict the matrix for zero cost matrix for each graph, even for those graph has not been measured with actual zero cost matrix. Then we train a conditional continuous normalized flow to sampling and modeling distribution for each condition. Then we can sampling from those, we can generate graphs from this conditional distribution based on this conditional continuous normalized flow. To evaluate our components of the graph autoencoder, we can see with semi-supervised learning, the latent space is much more organized. So it makes the graphs with similar performance that clustering together and more easily explored by the continuous normalized flow. However, if without the semi-supervised learning and the triplet loss, the latent space are not clustering well on with the model has similar performance. We test our generate process in the NASBench 201 and the NASBench 101. We can see our generated model has relatively similar performance as the reference model. However, it unlocks the potential to exploit the better model around the reference model. It's both observed in the NASBench 201 experiment and the NASBench 101 experiment. Also, to testify the more generalizability for our approach, we also tested it in the NASBench 316 to see if this approach can generalize well in the more diverse task. We can see we achieved the better performance than the reference model for every task in the NASBench 316.